Really, thank you to the organizers for inviting me to speak. It's a great pleasure to be here in Vilnius for this really nice colleague. And I'm going to be telling you something that continues on very nicely from all of the topology that we heard about in the previous talks. So I'm going to use that quite a lot in my introduction. But I'm going to be talking now about how we can go in a slightly different direction, up in dimensionality, to explore 4D topological physics, taking advantage of some of the recent advances in cold atoms and also photonics technology. And in particular, the thing that I'm going to be talking about today is this idea of synthetic dimensions, which came into cold atoms from the works of Maciek and Alessio and collaborators a few years ago. And the concept is very, very general and very beautiful. It's just that you take some set of states that you have in your system that are normally uncoupled, that you normally ignore, and then you decide to reinterpret that set of states as if they were a set of sites along an extra spatial dimension. And to do this, really what you have to add is some coupling to your system that couples those sites together. So this is the example of a kind of a next nearest neighbor coupling along this synthetic dimension that, because it's externally implemented, is very controllable and tunable. So, for instance, you can make those couplings to have complex hopping amplitudes. And so this is a really flexible way of implementing an artificial gauge field. And indeed, that was one of the things that they first proposed. And what really got me excited by this field was thinking, okay, if we're adding these extra dimensions to our system, this also allows us to start asking questions about what would happen in a 4-dimensional system or even higher, and think about it in a real, with the prospect of having real experiments to come after it. But I'm a theorist, so this is going to be a theoretical talk. And what I want to spend actually most of the talk doing is telling you about some of the cool things that we get in 4 dimensions. So to do that, I'm going to give you a brief reminder of some of the pertinent points of the 2D topological systems, a lot of which we've already heard today. And then I'm going to tell you about these sorts of 4D topological models and the differences that we can get in 4D. And then finally, I'll tell you a little bit about synthetic dimensions, setting the stage also for Leonardo's talk, who's coming straight after me and will tell us a lot more in that direction. So, the 2D quantum Hall effect, well, everything on this slide has already been shown today. I just want to highlight that in 2D, the quantum Hall effect is this linear quantized response that depends on the topological first Chern number. And that first Chern number can be calculated, as we've heard, as the integral of the Berry curvature of the block states of an energy band, if you integrate that Berry curvature over the whole of the Brillouin zone. And as we have also heard, this invariant in this, I'm considering just an equilibrium system, so it's a closed equilibrium system where this invariant is unchanged unless we do something that closes a gap between 2 of the bands. So for the purposes of this introduction, I just want to ask about how can we get a non-trivial topological transition in this type of model by looking at a seminal 2-band lattice model that we've also seen very briefly earlier. And in particular, I'm considering a minimal 2-band model that comes from having some sort of spinless particles or bosonic particles hopping on a lattice that has, say, 2 sites per unit cell. So this 2 bands are coming from some sort of bosonic degrees of freedom. And, okay, we have 2 bands. That means that we can generically decompose the Hamiltonian in terms of the identity and the Pauli matrices, where this D of k contains all the information about the specific system and is just a real 3-component vector. And so this is the vector of Pauli matrices. So that's just a 2-band model. And let's assume that we start with a trivial 2-band model. Well, how could we make it topologically non-trivial? We would have to have some sort of topological transition. So it would close a band gap and reopen it. And for the purposes of this talk, I'm going to consider the simple case where this closing and reopening happens at an isolated set of points in the Brillouin zone around which the dispersion is just linearly dispersive. And in particular, these guys are called Dirac points and Dirac cones. And this is just the linear dispersion. Apologies about the resolution. I had to change the resolution to fit the slide, so I hope it's not too pixelated for you to see. And it just depends on sigma x and sigma y in this formulas. And now, how can we close it? So this is when it's closed. How can we open it and tune through a transition? Well, to do that, we have to add the other Pauli matrices that's missing, the sigma z, and that will open a gap at this Dirac point. It's very easy to see. This is just a two-band model. You diagonalize it, you see that this m term will give you a gap. So to go through a transition, we could just use this m as a smooth tuning parameter to go from negative to positive values, such that we tune it through this transition. But what does this do to the topology or geometrical properties of our system? Well, we can calculate the Berry curvature, and indeed this Berry curvature, as we've already heard today, is, in the case of a two-band model, has a very nice interpretation as a topological charge density that's basically taking a local vector defined with respect to your Brillouin zone and seeing how it maps onto the 2D Bloch sphere. So if this covers the Bloch sphere, then you have a skyrmion in the lower band, and that's what the Chern number is for this system. But I just want to use the form of this, because if you look at how this is affected by going through a transition, you see that the Berry curvature is going to flip its sign as you go through, because your DC, this third, well, your D3, one of the components is flipping the sign. So you're going from minus m to positive m. But then there are two possible choices. One type of Dirac cone will, as you go from negative m to positive m, will increase the Berry curvature. And the other type of Dirac cone will decrease the Berry curvature. And this will depend on whether those other components of your Hamiltonian have got the same sign or have got opposite signs, as you can just see from that. And this has important consequences when you're thinking about what topology you can have because of symmetries. So in the particular case of having time reversal symmetry for a spinless particle, then that tells us that h star of k has got to be equal to h of minus k, and that d vector was real. So sigma x and sigma z are also real. So that just translates to saying this condition at the top. But sigma y is imaginary, has those eyes, and so we have a different condition on the second component of that vector. And this means that if you think about having a Dirac point at k, then at minus k, you will also have a Dirac point, but it will have an opposite type, because it will have to have a different sign for this second component. So if you think that this guy is going to, say, increase the Berry curvature, but then this guy will also decrease the Berry curvature. So if you have time reversal symmetry for the spinless particles, and you calculate a Chern number by going through a transition of gapping out these Dirac cones, because you have to gap them out together to preserve time reversal symmetry, you will get something topologically trivial. And that's actually just a very specific example of something which is much broader, which is in 2 dimensions. You need to break time reversal symmetry to have the 2D quantum Hall effect. So this was demonstrated very beautifully by the Haldane model, which we've already heard a bit about today. I've just drawn it here for a brick wall lattice rather than a honeycomb lattice. So this is just kind of equivalent, because you can just get one from one to the other by just squishing it a bit. And you can see that if you have time reversal symmetry, there are 2 Dirac cones in the Brillouin zone. This is a pair. And to get something topologically trivial, you have to add something else, in this case, complex next nearest neighbor hoppings, which allow you to isolate just one of the Dirac cones. Because if you gap them out together, you'll get something too trivial. And of course, that's much more general for multi-band models. Breaking time reversal symmetry is at the heart of having Landau levels and the Hofstadter model, which describes a particle hopping on a square lattice in the presence of a magnetic flux. So that was a few points that I want to highlight about 2D quantum Hall. What about the 4D topological physics? What changes, or what is the same in 4D? Well, in 4D, we actually have a new topological invariant coming out. So we already actually saw the d-dimensional form of this. So if you remember that, this is not so much of a surprise. This is now in 4 dimensions. We have this invariant which can be written for mathematical people as a wedge product of that Berry curvature 2 form. Or if you prefer, this is for the non-degenerate band case as this product of all of these Berry curvatures. And these Berry curvatures, you can see they depend on, in total, this product has 4 indices, x, y, z, and w, so it's not going to be there in fewer dimensions. And then, if you go to 60, you would get the 3rd Chern number and a 60 quantum Hall effect, and so on and so forth. So this new topological invariant is one of the key things that we get coming in the 4-dimensional quantum Hall effect. And also the effect itself is a little bit different. So I'm going to just illustrate this with really the simplest model, which is actually a 4D Harper-Hofstadter model. So I showed you a couple of seconds ago the 2D Hofstadter model, which was just the particle on a square lattice in the magnetic flux. This is now a particle on a 4D square lattice, well, hypercubic lattice, in the presence now of 2 magnetic fluxes through these 2 planes, which will give you just this part of the expression being non-zero. And in particular, this model has the nice property that you can decompose that 2nd Chern number as a product of the 1st Chern numbers. And this is really nice because it gives us a very simple way to understand the 4D quantum Hall effect that emerges. So we have to apply 2 perturbations. That's a difference to the 2D. So now we have 2 perturbations, not 1 perturbation. Also this magnetic perturbation we need. And that's because if we just start in one of these planes, the xz plane, and we apply this electric field, then we have a Berry curvature xz. So that's just going to give us a Hall current along x. That's just a 2D quantum Hall system on its own. But now this extra perturbation, what it allows us to do is to couple this Hall current to other planes of the system. So this current flowing in the presence of the magnetic field, the magnetic perturbation, will give you this Lorentz force, and that, because we also have a Berry curvature in this other plane, will lead to another Hall current. So in total, you will end up with a response along y to these perturbations that depends now on the 2nd Chern number. And you can kind of see it's coming here quite clearly from this product of the 2 Chern number responses. But this is the simplest case. It can be more non-trivial than that. I just don't have the time to show you, but hopefully you get a flavor. So a key difference here is this is a nonlinear response that depends on the 2nd Chern number. So this is not, though, the only kind of 4D quantum Hall system that we can have. So whereas in 2D, this is, I should just say, so this is a topological classification of gapped and non-interacting fermion systems according to the symmetries and the dimensionality. And the 2D quantum Hall is this class here, where you've broken time reversal symmetry, you don't have other symmetries, and you're in d equals 2. And you have a z, that's the 1st Chern number. What I just showed you on the previous slide is this guy in 4D, so it's still a z, but there are other z's in this 4D column. And those other classes here that I've just highlighted also give you 2nd Chern numbers and a 4D quantum Hall effect, but with other symmetries. So in particular, the 4D quantum Hall effect was actually first proposed in the context of time reversal symmetry for fermions, which corresponds to this class. And something that I've done very recently is to show how we can actually think of a 4D quantum Hall effect in this class, which is class A1, which has that spinless time reversal symmetry I was talking about before, and which, as you see, is actually topologically trivial in the lower dimensions. This is something that will only be topologically non-trivial once we've got to 4D, just by using the lattice conductivity. So this proposal doesn't need any gauge fields. It's just coming from the lattice. And that's what I'm going to explain very briefly to you now. And it follows very directly from the example I gave you in 2D. So whereas in 2D we had a 2-band model, in 4D we're now going to consider a minimal 4-band model. And this, instead of being Pauli matrices, these are now gamma matrices, which I've written out at the bottom in the basis that I used for anyone who doesn't work with them that often. And again, you can see we can have these 4D Dirac cones, which have linear dispersions with respect to the 4 momenta, and then a mass at the end. And so just as before, we can talk about the second Chern number. And now the second Chern number is a higher order topological charge density integrated. So it's a higher winding number, now associated with a spin 3/2 sphere. And we can do the same game again. So that mass is going to be closing and opening a gap. And we can say that as this is used to close and open the gap, we will have 2 types of these Dirac cones. The first will increase the integrand, and so will contribute positively to the second Chern number. And the second type will decrease it. And that depends on the relative signs with respect to these other components of the vector. And now spinless time reversal symmetry will lead us to these conditions. So they're basically the same kinds of conditions as we had in 2D, but we just have an extra condition for the component with respect to the next kz and another one for kw. But here you can see that we have 2 complex gamma matrices, and this means that now a time reversal, a point at k, will actually be the same type as a Dirac point at minus k, because they differ by 2 minus signs. And this means that one consequence is, as you can see, the second Chern number for this class is actually even integers, because we changed the second Chern number by 2 by gapping out these Dirac cones. And we can preserve time reversal symmetry and gap out these cones together. And actually, I'm just going to flash very quickly the model that I propose to do this, which is very much inspired by what we saw from 2D, the Haldane model, and is now a 4D kind of Haldane model in some sense, where we have a 4D brick wall or 4D honeycomb lattice, which is made up of hopping terms and then an on-site energy term. And this will give us 2 pairs of time reversal related Dirac cones in the Brillouin zone. So this is at m equals 0. But if we have nothing else, it will be topologically trivial. So this is just the integrand plotted on either side of that transition. And you can see it cancels out. This is for a particular cut, but you can, of course, look at its behavior over all cuts to see the actual Chern number. So what you need to do, just like in Haldane, is you need to add some extra longer range terms. But now those longer range terms don't have to be complex. They can be real. They can preserve time reversal symmetry. I'm not going to go into much detail about what they are, but just to say that if you choose the right type of terms, you indeed can gap out just a pair at a time to get, or gap out one pair, and then at another point the other pair, and in between you will have a topological region. So just to summarize, the 4D quantum Hall has got these other topological invariants, a nonlinear response, but also we have a wealth of different topological classes, including some classes that are genuinely new physics that's coming through in 4D and that extends some of these ideas from things like the Haldane model. So in literally the last 3 minutes or so, 2 minutes, just to flash then, why am I talking about this at a Cold Atom conference? It's because I really hope that synthetic dimensions will allow us to build these kinds of models in the lab. So this is what I said a synthetic dimension was. The question I haven't asked or answered yet is how. As Leonardo will tell us, I think, he'll tell us, one way to do this is by coupling together the different atomic states to act as a synthetic dimension. Another way that we've proposed is to do this by shaking a harmonic trap. So the harmonic trap states give you a synthetic dimension. And Grazia has a poster on this, on the latest work on this. So go and see her poster to find out where this is going. And there's also many proposals and a very recent experiment in photonics that go in the synthetic dimension direction. So you do 4D quantum Hall, therefore, by literally building a system that includes these hoppings along the synthetic dimension. And the final advert is just to say this isn't the only way to explore 4D quantum Hall. You can also use topological pumps. And that's something that I'm leaving to Oded Zilberberg to explain in his talk tomorrow. So with that, I'd just like to conclude. I've told you a bit about topological physics in 4D. I mentioned briefly some directions that are given by synthetic dimensions. I also do have a PhD position available in my group. So if you know someone who's very good master's student, direct them towards me. And we also have a recent review on topological photonics. And so thank you very much to all of my collaborators, and thank you for your attention.